So we're going to talk a bit about stationary points, and I've deliberately put this diagram onto the screencast so that you can refer to this diagram. Because the first thing you need to know is what a stationary point actually is. So when I refer to a stationary point, I'm asking you to identify points where you have a flat section on the graph. You can see A, B, C, D, E and F all represent flat sections on these quartic graphs. So they've got potentially, they're quintic graphs because they've got those flat bits. So on these graphs, those flat sections represent stationary points. So I'm going to write that here. Now, some of those stationary points are turning points and some are points of inflection. So I'm also going to classify those so that you've got that knowledge. So a turning point, which because you've done quadratics, we will often just call TP, are points where the actual graph turns around and starts heading the other direction. So we have a turning point here and a turning point here, A and C. We also have turning points at D and E. And you'll notice that A and D, they are called maximums. No, that's completely wrong. My apologies. A and F are maximum turning points. So just take a second to think about why they would be maximums. They are the peak of our graph. So they represent the maximum. And obviously C and D are minimum turning points. And from now on I'll call them max and min. They're also sometimes defined as local minimum and local maximum. If you've got more than one, you'll define that the local, around a point, say x equals 2, there is a minimum occurring here. That's the local minimum. There might be another one somewhere else on the graph, but that is the local one. So you'll hear them referred to as local minimum and maximum as well. So that's stationary points. I'm going to talk a bit more about points of inflection on Monday, so you don't need to worry too much about that. But basically a point of inflection is where it gets flat. Now let's just have a quick look at the gradient nature of a stationary point. So first of all, if I define my function as y equals some function of x, and then I derive y, and it's equal to the derivative of that function of x, the stationary points, SP, and in this case I'm going to talk predominantly about turning points, occur when y dash equals 0. Because y dash is the gradient function. It represents how steep the curve is. And when the curve has a steepness of 0, it must be flat. And when it's flat, you have a stationary point. So when y dash equals 0, you have a stationary point. We've talked about this before. So that means to find a stationary point, you just need to derive the function and then let the derivative equal 0. Bam, you've got a stationary point. You might have more than one, so you might be deriving a cubic to get a quadratic. Solving, you'll get 2 stationary points because the solution of quadratic can have up to 2 solutions, 2 answers. So that's how we find our stationary points. The other thing is you might need to classify your stationary points. So to classify, and sometimes this is called finding or determining the nature of a stationary point. So there are 2 ways to determine the nature of a stationary point. The first way is to do a gradient table, which I'll talk about predominantly today. So a gradient table looks at what is the gradient as we approach the stationary point from below, and what is the gradient as we approach the stationary point from above, and what shape does that form. So let's have a look at an example. Let's say that there is a stationary point at x equals 2, and we're going to look at the gradients. Now we know because there's a stationary point at x equals 2, the gradient is 0. Now let's look at it below. X equals 1.9 and x equals 2.1, for example. We get close. We just need to make sure we don't get our points that we choose mixed up with other stationary points. So make sure they're close enough that they're not really too close to other stationary points. And let's say that at 1.9 y dash is positive and at 2.1 y dash is negative. Diagrammatically, that means that our stationary point is flat here. On the approach from below, it's got a positive gradient. I don't care what that gradient is. I just care that it's positive. And an approach after, from above, we have a negative gradient. And you can see, if we have a positive, flat, negative, that creates a local maximum. So if we do a gradient table and test that gradient table, we will be able to identify straight away whether it's a maximum or a minimum. There will be times where you could identify that from the context, or it might be a quadratic function and you know because it's a positive a value, then it's a bowl shape, a smiley face, and therefore it's only got a minimum. But really you should test the nature of stationary points in all cases anyway. So that first one is gradient table. That's number one. The second is the second derivative test. And so this is number two. Now, if the first derivative defines the rate of change of the function, the gradient of the function, the second derivative defines the gradient of the gradient function, the rate of change of the gradient function. So now, this won't be on the screencast, but I'm going to show you with my hands, and you'll want to watch this, and I'll do this a lot. This is a bit like one of my dance moves, okay? If we're talking about a maximum, the gradient starts positive, and it goes to 0, and then it becomes negative. So what's the rate of change of the gradient for a maximum? It's going from positive to negative, which means the rate of change is a decreasing, isn't it? It's a decreasing rate of change. So the rate of change will be negative. That means that if we have a maximum, d squared y dx squared, which is also known as y double dash, will be negative. It means that the gradient is going from a larger number, a positive number, to a negative number. That means that the way it's changing must be negative. It's negatively changing. And equally, if I have a minimum, I start negative, I go to 0, and then I end up positive. So that means that the second derivative, the rate of change of the rate of change, is now positive. It's going from negative to positive, so it's changing in a positive direction. And so with my hand, I'm either scooping down or I'm scooping up. And that scooping down or scooping up defines whether I've got a second derivative that's positive or negative. So for minimum, I have d squared y dx squared is equal to y double dash, and that's positive. So let's look at a couple of examples. I'll do these examples, I'll overdo the examples. So I'm going to basically do the solution, find the turning points, and then we're going to test the nature of those turning points with a gradient table and a second derivative. So example number one. So let's say we're talking about a quadratic. Y equals 2x squared minus 4x plus 7. And I want to find and define the nature of the stationary points for this quadratic. So the first thing I do is I calculate y dash, and that's equal to 4x minus 4, and I let y dash equal 0, which means that I get 4x minus 4 equals 0, and that gives me 4x equals 4, and x is equal to 1. So I'm letting the derivative equal 0, and I'm rearranging to calculate the x value when that equals 0. There's only one solution, so there's only one turning point, and there's only one turning point because it's a quadratic. So we already knew there'd only be one turning point. Now test number one would be the gradient table, GT, and my gradient table test will be start at x equals 1, and we'll use x equals 0.5 and x equals 1.5. Now at x equals 1, I know that I've got a gradient of 0, so that should be y dash. At x equals 0.5, remembering that y dash is equal to 4x minus 4, at x equals 0.5, that gives me negative 2, and at x equals 1.5, that gives me 2. So I have a negative gradient, 0 gradient, positive gradient, and therefore I have a minimum function. Gradient table, really simple way for any function to define whether it's a minimum or a maximum. When we get into next year, some of the functions we're deriving, we will be deriving them using chain or product rule. They will be complex. If we've used the product rule, we've already split it into two terms because we have u dash v and v dash u. And then to find the second derivative means you'll end up with 4 terms. It gets a bit out of hand. There will be times where it's very suitable to go with the analytical method rather than the algebraic method and choose to use a gradient table. It will save you a lot of time and it's perfectly reasonable. But it can be quicker to use the second derivative as well. So I'll call that the second d. And so my y double dash is equal to 4, because y dash was equal to 4x minus 4. And the second derivative is positive in all cases, which implies that this is a minimum. Because remember, if we go back to our definitions, a minimum has a positive second derivative. So in this case, because it was so easy to derive that function again, the second derivative was the easiest test to do. If it's an easy function to derive, go the second derivative. If it's going to get complex and out of hand deriving it, go the gradient table method. They're your two choices. At times in the assessment, we might specify what you need to use, so you must need to be able to do both of them, but a lot of the time you'll just be able to choose what you use and how you want to use it. Second example, and this is the one that we made up earlier. Y equals x cubed minus 6x squared plus 9x minus 2. So it's a cubic. We're expecting two turning points or possibly a point of inflection. If there's a point of inflection, it eradicates, it cancels out two possible turning points, that point of inflection. So, first of all, I calculate my y dash is equal to 3x squared minus 12x plus 9, and I let y dash equals 0. Be careful not to do something like this. Communication-wise, it's really better not to have two equal signs on one line, because that creates a different mathematical statement. So try and stick with doing one on each line. And I'm also heading to having my y dash and my algebraic term on the left-hand side. X squared minus 12x plus 9 equals 0. I'm going to divide both sides by 3 to give me x squared minus 4x plus 3 equals 0. And this is x minus 3, x minus 1 equals 0. And I can solve that by saying that x is equal to 3 or 1. Now you know, if you understand the shape of a cubic here, you know that there is no way there can be any result except one of those is a minimum and one of those is a maximum. There can't be two maximums or two minimums. You know one is a minimum, one is a maximum. What I'm going to do is I could use the gradient table, and in fact I'm going to skip that in this case, because in this case it's much easier to use the second derivative. So I'm going to go straight to the second derivative to test the nature of my turning point. In this case, y double dash is equal to 6x minus 12. I had a quadratic, it's now gone to a linear function. And at x equals 3, y double dash is equal to 6 times 3 minus 12, which is equal to 6. That's positive, and therefore it's a minimum. And at x equals 1, y double dash, now I already know this has to be a maximum. The shape of a cubic defines it. Really, I can't have a minimum here. But 6, 1 minus 12 is equal to negative 6, which is negative, which implies a maximum. And I can go from there. Now, if I had to sketch this very quickly before I finish, if I had to sketch this function, I would know there's a turning point at 1, a turning point at 3. I would know that it has a y-intercept of 2. So I'd know my turning point at 1 was a maximum, so I'd know it looked something like this. If I substituted x equals 1 and x equals 3 into my original function, I'll be able to calculate the coordinates of my turning points as required, and there's really nothing else I need to know.